At some point in time, you've probably played with magnets. Those two little objects that you bring together and they repel each other or stick together. So we really want to look at what is a magnet. Well, a magnet is an object whose atoms are arranged in such a way that they can actually create a force on the atoms of other materials. There are lots of different shapes and sizes of magnets, but in order to be a magnet, an object must contain a south pole at one end and a north pole at the other end. If you take a bar magnet and place it in the midst of some iron filings, you will see a definite pattern begin to emerge within the filings that are attracted to the magnet. Around each end of the magnet, the filings are all pointing out from the magnet. If you look at that arrangement, you may notice that it has the same general pattern as our electric fields. The reason the iron filings are pointing around the magnet is because the magnet induces magnetism into each little tiny piece, and those pieces essentially become lots of little tiny magnets. If we look at this at the microscopic level, what we see is many regions with an unmagnetized piece of iron, where the poles are pointing in all directions. If you bring a magnet close to the iron, the fields inside will begin to align with the magnet and reform into different domains until eventually they are all aligned. If you were to take a compass, which is basically just a little magnet, and bring it close to a bar magnet, it would point away from the magnet at the top. As you move the compass down, the direction of the compass needle changes direction as it aligns with the magnetic field. When you get down to the bottom, the compass needle will point towards the magnet. So the compass will allow you to determine the direction of the magnetic field produced by the magnet, just like our small positive test charge allowed us to determine the direction of our electric fields. Experimentation shows that all magnets have two poles, a north-seeking pole and a south-seeking pole. As with charges, like poles repel each other and opposite poles attract each other. So bringing the north poles of two magnets together will create a magnetic force that will act to repel the ends of the magnet. The same thing will happen if you bring the south poles of the two magnets together. However, if you flip one of the magnets around so that the north pole of one magnet is brought near the south pole of another magnet, the magnetic force will attract the two ends. What's really pretty cool is that just like charges cannot be separated, north and south poles of a magnet cannot be separated. You can start off with a large magnet, and if you cut it in half, you will end up with two smaller magnets, both of which have north and south poles. Cut these magnets in two, and the same thing will happen. Keep on going, and eventually you would end up with an iron atom with a north and south pole. Now, just like we used an electric field to describe electric forces, we can use a magnetic field to describe magnetic forces. Magnetic forces act over a distance. In other words, two objects do not need to be in contact with each other in order for magnetic forces to have an effect. So we can draw the magnetic field around any given magnet. If we take our bar magnet, the field will be coming out of the north pole and going into the south pole. This happens on all sides of the magnet and creates a three-dimensional field. Unlike electric fields, which begin and end on the charges themselves, a magnetic field line will extend through the center of the magnet, forming a closed loop. Now, if we take two long flat magnets and align them so that the north pole of one is aligned with the south pole of the other, the magnetic field in between them is assumed to be constant or uniform, which means that the magnetic force will also be uniform. In reality, this is not easy to produce over a large area. Also, notice at the edges the field fringes out a little bit. The magnetic field lines are not quite parallel or uniform.